plus 2 electrons. So this one is an oxidation reaction, which means to say that our zinc is being oxidized to zinc 2 plus by losing 2 electrons. But we are saying that this one, our zinc, is our reducing agent. From the definition of a reducing agent, we say that a reducing agent is a substance that causes the reduction of another substance, but it itself is being oxidized in the course of the reaction, which means an oxidation reaction, that is where we are going to get our reducing agent. Then the oxidizing agent now is written on the right hand side. So as you can see on our cell notation there, on the right hand side, that is where we are going to find our oxidizing agent, because we are saying that an oxidizing agent itself by definition is the substance that causes the oxidation of another substance and is itself reduced in the course of the reaction. As you can see, our hydrogen ions are being reduced to hydrogen gas by gaining 2 electrons. So what we are having is there is need for us to write our chemical reaction. Our hydrogen ions are being reduced to hydrogen gas. So this one in itself, it's a reduction reaction. Why? Because we are gaining electrons there. So our hydrogen ions plus 2 electrons, we are producing hydrogen gas. So this one is a reduction reaction. So since it is a reduction reaction, we see to that our hydrogen ions are being reduced. So if they are being reduced, so they are acting as an oxidizing agent. So it causes the oxidation of our zinc to zinc 2 plus, but itself is being reduced in the course of the reaction. And same applies with our zinc there. Our zinc solid causes the reduction of our hydrogen ions to hydrogen gas, but itself is being oxidized. So this one is a reducing agent and this one is an oxidizing agent. So don't confuse the two particular reactions, right? And then apart from that, we are saying that the standard potential difference of the cell can be found from the equation. So we are saying that if we want now to actually find our, if we actually want to find now our, if we want to actually find our electrode potential now, we are saying that our electrode potential of our cell, which we are writing like this, electrode potential of the cell is going to be equal to the electrode potential of the oxidizing agent minus the electrode potential of the reducing agent. At times it can also be written as the electrode potential of the cell is equal to the E of the cathode minus the E of the anode. So these are the two particular equations which we normally use when we want to calculate our electrode potentials. So, and the electrode potential of our cell itself is being measured in volts, and our electrode potential is the standard reduction potential of the cathode in volts, and then the electrode anode or reducing agent which we have there is the standard reduction potential of the anode in volts. So the reading on the voltmeter, which we are actually going to see in this case, we have the reading on the voltmeter which we are going to see. That one itself is about 0.76 volts with the zinc electrode connected to the negative terminal. This indicates that the standard electrode potential of the zinc electrode will be minus 0.76 volts. The galvanic cell formula is written this way because the zinc loses electrons to the hydrogen. Calculation of the standard electrode potential of the zinc solid to the zinc 2 plus half cell is done as follows. So we're having our equation here. Our E electrode potential of our cell is equal to the electrode potential of our cathode minus the electrode potential of our anode. So we see to it that our E potential of our electrode potential of our cell is 0.76 volts will be equal to the electrode potential of our cathode, which is 0.0 volts, minus the electrode potential of our anode, which is our zinc being converted to zinc 2 plus. Right? So that is what we have. If we are going to do our mathematics correctly, we are going to see to that we are going to have 0.06 volts is equal to minus the electrode potential of the zinc half cell. So if we're going to do the calculation, the electrode potential for the zinc is going to be equal to minus 0.76 volts. So if a copper half cell was set up in the same way, the reading on the voltmeter itself will be different with that one of the zinc. We will see to it that this one itself, we're going to have our electrode potential of our cell, that is of our copper cell itself, is going to be equal to the electrode potential of the cathode, or that is minus the electrode potential of our anode. Right? So, but now the electrode potential, if we're going to use our voltmeter in the case of a copper half cell, this thing was done experimentally, and as a result it was found that the voltage there is minus 0.3 volts, that is of our cell. Right? And then we'll be using our standard hydrogen electrode. So our voltage there for our cathode is 0.00 minus the electrode potential of our copper, and we see to it that our copper itself, we are going to have the electrode potential of the copper will be equal to minus divided by a minus will give us a positive. So we're going to have 0.34 volts. So we can find the electrode potentials of n of the chemicals using these particular cells. So we can find any of the chemicals. We can take aluminium, we can take any of the chemicals which we have in the periodic table, and at the end of the day we can find their standard electrode potentials. So this is one of in fact this is the way how we find the standard electrode potentials. So initially we're supposed to have our standard, which is the hydrogen cell, and then we're supposed also to have that one of our metal electrode. So at the end of the day we are going to compare the electrode potentials of the two, and then we can actually find our electrode potential of our metal. So this is how standard electrode potentials are being obtained, and we are going to use them in the next lecture. That is when we are going to focus our attention on the use of these standard electrode potentials, when we are going to use our standard electrode potential tables to actually find some of these electrode potentials of our chemical reactions. So with this lecture number 4, stay tuned for lecture number 5.